Let's do one more example of calculating the percent yield of a reaction. In this case, we want to calculate the percent yield of a reaction where 106 grams of sulfur dioxide was produced from the reaction of 78.1 grams of carbon disulfide with 83.8 grams of oxygen. The other product of this reaction, as we need to know, is carbon dioxide. So to find percent yield, which is what the question is asking, we need to find two numbers, the actual yield, theoretical yield. That ratio times 100% is the percent yield of this reaction. So to do that, we need to start with a chemical equation. And so our chemical equation tells us that we have our two reactants, carbon disulfide and oxygen. So carbon disulfide, two sulfurs, one carbon, reacted with oxygen. We have to remember that oxygen is one of the 7 diatomic elements. So it's not O, but rather O2 is its formula. That produces then sulfur dioxide as one product, sulfur dioxide, one sulfur dioxide, 2 oxygens, and then the other product has to be carbon dioxide. 1 carbon, 2 oxygens. So now we have our equation. In order to be able to use this equation, though, we need to make sure it's balanced and not balance it. So notice we have 1 carbon, 2 sulfurs, 1 sulfur, so we know it's not balanced, 2 oxygens, and 4 oxygens. And so we can go about balancing this a couple of different ways. Probably the easiest way to start, though, is by putting a 2 in front of SO2 to balance the sulfurs. When we do that, notice that we now have 4 oxygens plus 2 oxygens, now 6 oxygens. And because the oxygens come in pairs on the reactant side, we can have also equivalently 6 total oxygens by putting a 3 in front of the O2. So now we have a balanced equation, which tells us that 1 mole of carbon disulfide reacts with 3 moles of oxygen to produce 2 moles of sulfur dioxide and 1 mole of carbon dioxide. So if we kind of apply our numbers here to give us an idea of what's going on, we have 78.1 grams carbon disulfide reacted with 83.8 grams of oxygen, and that produced 106 grams of sulfur dioxide. So this is how much we started with the reactants. This is how much of one of the products we actually, in fact, produce. So this number, 106 grams, this is the number given to us as a problem. And so that number then must be the actual yield of the process. So that's going to be our numerator ultimately in our percent yield equation, equation 5.2. To find the percent yield, though, we need to find the theoretical yield of this reaction. It's going to take quite a bit more time because theoretical yield is how many grams of sulfur dioxide should we have been able to produce from the reaction of 78.1 grams of this reactant with 83.8 grams of this reactant. Notice that because we have 2 reactants, we are given the amounts of both reactants. This is a so-called limiting reactant problem where we have to determine between 78.1 grams of carbon disulfide and 83.8 grams of oxygen, which one is the limiting reactant, which one's going to run out first, because it's the amount of that substance, whether it's this substance or this substance, that's going to determine the theoretical yield of the reaction. So to do that, there's a way you can approach these limiting reactant problems. The method that I like is to simply assume that the first reactant is limiting. So we're going to assume here that carbon disulfide is your limiting reactant. And then our plan is that we're going to then go from grams of carbon disulfide to moles of carbon disulfide to moles of oxygen to finally, I'm sorry, not moles of oxygen, rather, but moles of sulfur dioxide to grams of sulfur dioxide. So we're going to first do that stoichiometric calculation, grams of one substance, this reactant, 2 grams of the other one of the products, SO2. And then we'll do the same thing. This time, assume that the oxygen is limiting reactant. So we know one of these 2 is going to run out first, so we just kind of approach and kind of investigate both possibilities. for the same idea plan here. So we'll go from grams of oxygen that we actually used to moles of oxygen to moles of the product we're interested in, SO2, 2 grams of SO2. This is our typical stoichiometric approach, calculation approach, grams of one substance, grams of different substance, grams of moles, moles of moles, moles of grams. And then we'll get 2 answers. Notice that we'll get mass of SO2 that I should produce, assuming that O2 is a reactant. I'll then also get mass of SO2 I should produce, assuming CS2 is our limiting reactant. And then with this approach, whichever of these 2 answers is smaller is in fact the theoretical yield, because it's based upon the correct assumption. So in order to do this, of course, we'll use our balance equation for the mole-to-mole conversions. And then we'll need the molar masses or the grams of moles and moles of mole conversions. So I've already calculated molar masses of these substances. We have 76.13 for CS2. So grams of moles, we have 76.13 grams equals 1 mole for CS2. For SO2, we have the conversion factor of 64.06 grams equals 1 mole. Of course, that's the same for this calculation. And then finally, we need grams of oxygen, moles of oxygen, and that's the fact that 1 mole of oxygen, O2, is equal to 32 grams. So 32 grams equal to 1 mole of oxygen, 76.13 grams equal to 1 mole of CS2, and 64.06 equal to 1 mole of SO2. So those are all the numbers that we'll need in order to do our calculations. So if we now do those calculations, we have number 1, let's follow along. We have grams CS2, 78.1 grams of CS2. Convert that to moles, so go from grams to moles. You need to divide by the molar mass to 76.13 grams. Then go from moles of CS2 to moles of SO2. This is our balance equation coefficients. So from the balance equation, notice that we said it takes 1 mole of CS2 to produce 2 moles of SO2. So it's a 1-to-2 ratio. So for every 1 mole of CS2 that's present, we should produce 2 moles of SO2. And finally, moles of SO2 to grams of SO2. We'll use the molar mass of SO2, which is 64.06. Now we can calculate to predict how many grams of SO2 we should produce, assuming that this is correct, that the CS2 in fact will run out first. So 78.1 times 2 times 64.06 divided by 76.3 gives us the value of 131.435 grams of SO2. That's how many grams of SO2 we should produce if this in fact is a reactant. So to check that assumption, and we can do the same kind of calculation, except now we're going to start with the amount of oxygen. And we're saying that the oxygen runs out first. So we have 83.8 grams of oxygen. So the same approach, grams of moles, moles of moles, moles of grams of oxygen. 1 mole of oxygen, O2 is equivalent to 32 grams of oxygen. Now for our balance equation, notice it takes 3 moles of oxygen to produce 2 moles of SO2. So this is a 3-to-2 ratio. So 3 moles of oxygen is required to produce 2 moles of SO2. And then finally, converting from moles of SO2 to grams of SO2, we'll use that same molar mass, 64.06 number. Using calculations now, we have 83.8 grams times 2 times 64.06 divided by 32 divided by 3 gives me a value of 111.84. 83.8 grams of SO2. So to take a pause here, we've calculated that assuming that all 70.1 grams of CS2 rather is able to react, in other words, assuming that CS2 is the linear reactant, we should expect to produce a little over 131 grams of SO2. But assuming that the oxygen linear reactant, assuming that all 83.8 grams of oxygen is able to react, we would only produce about 111.8 grams of SO2. So we can see then that based on our calculations, that the correct assumption is the second one, because we predict less product compared to the first assumption. So this number not only allows us to predict linear reactant, but this number actually is in fact our theoretical yield. It's how much SO2 that we should produce based upon the stoichiometry and based upon the amounts that we started with. So to actually finally answer our question, okay, percent yield is going to be our, specifically here, it's equal to the actual yield. In this case, the only actual yield given is the mass of SO2, so 106 grams. Of SO2 was produced compared to how much should have been produced, which is, according to our calculations, based upon the fact that oxygen in this case is a linear reactant, 111.838 grams of SO2 times 100%. Notice that with our percent yield calculations, not only are the units for actual yield theoretical yield, those must be the same, so they're in this case they're both grams, but it also has to be describing the same thing. So in this case, grams of SO2 that we actually produce compared to grams of SO2 we should have produced. If I were given instead, if I were given the amount of carbon dioxide that actually was produced in this reaction, then all my calculations here are based upon predicting how much carbon dioxide I should be able to produce. In this case, we have SO2 in both cases. So finally, we can just take the ratio. So our 106 grams, looks like we have 3 set figures divided by 111.38 times 100 gives me a percent yield, quite high percent yield of about 94.779, so 94.8% yield. So according to my calculations, that we only produced slightly less than 95% of the product that we should have been able to produce.